Okay, soon we're going to talk about solving linear inequalities involving one variable. And the solution to linear inequality involving one variable is generally a set of numbers rather than a single number. So before we get into solving those linear inequalities, let's talk about how we represent those sets of numbers. So right here, you may be familiar with the set builder notation. Here, if you read this, it reads x such that x is greater than some number a. So an example of that would be right here where you have x is greater than the number 3. Well, in interval notation, which you might not be familiar with, in interval notation you would start with the parentheses 3 and then put a comma there, and then it tells you you're going to go out to infinity. And so if you were to graph this solution set, you would start at the number 3, and then you would shade to the right, and you would put an arrow here to show that it goes on forever and ever. Now, where you start here, right here, you can use a parentheses opening in the direction of the arrow, or if you look behind it, you can see there's an open circle. Now, I prefer to use parentheses and brackets, whereas other texts might use an open circle and a closed circle. Now, let me explain what that does. The open circle or the parentheses lets you know that the number that's here, the 3, is not part of the solution. Whereas if we used a bracket or a closed circle, that would tell me that the number 3 here is part of the solution. So for instance, if we wanted to do one that said x such that x is greater than or equal to a, like for here I would have x such that x is greater than or equal to 3, then the interval notation for that, since we're starting at 3 and we're including 3, we would use a bracket, and then it would still go out to infinity like the previous example. So we would basically shade the same region, except we would show that we're going to include the number 3 by using a bracket or the closed circle. Now, if you want to talk about values that are less than some number, like here it says x such that x is less than a, for example, x such that x is less than 6, well then we would actually start at negative infinity, and we would put a parentheses there. You never put brackets to block off infinity or negative infinity. So we put a negative infinity, comma 6, since 6 is not included in the solution, we would use a parentheses here, and so we would start at 6 and then shade everything to the left of 6, and again the arrow shows that this goes on forever and ever to the left. And again, the parentheses or open circle implies that 6 is not part of the solution, whereas if you have x is less than or equal to 6, then you would use a bracket with the 6 because that implies that 6 is part of the solution. So the only difference between the previous graph would be that when you start here, you would either use the bracket or the closed circle to show that the 6 is part of the solution. Now, if you wanted to talk about a set that falls between two numbers, we could do it this way. We could say all x such that x is greater than 2 and less than 6. Well, since x is greater than 2 and not equal to 2, we would put a parentheses with the 2. And since x is just less than 6 but not equal to 6, we put a parentheses with the 6. So this represents all values between 2 and 6. On the number line, we would put a parentheses at the 2, and we would put a parentheses at the 6. And notice they're going to open toward the shaded region, and we would shade the region between 2 and 6. Now, if we wanted to include both of these points, then we could write x such that x is greater than or equal to 2 and less than or equal to 6. In that case, we would put a bracket on both ends. So we'd have a bracket with the 2 and a bracket with the 6, and accordingly we would have the brackets on the number line here that encloses the region from 2 to 6. So up here, the 2 and the 6 are not part of the solution, whereas here, the 2 and the 6 are part of the solution. Now, what if we wanted to include only one of the endpoints but not the other? Well, then, like for instance, what if we wanted to include the 2 but not the 6? well then we would say x is greater than or equal to 2 and less than 6. So we would include the bracket with the 2 since it's part of the solution, but not with the 6. And so if you graph that, you would have a bracket, like I said, with the 2, but a parenthesis with the 6. Or you would include a closed circle with the 2 and an open circle with the 6. And then if you want to flip-flop that, suppose you want to include the 6 but not include the 2. So here you have x is less than or equal to 6 and x is greater than 2. Well, then you would put the bracket with the 6 and the parentheses with the 2, and the same thing on the number line, the parentheses with the 2 and the bracket with the 6. And again, you shade everything between those two, but here the 2 is not included in the solution and the 6 is included in the solution. Now, these actually are considered to be compound inequalities. These 4 that I just did are actually compound inequalities because they actually could be represented with 2 inequalities. But you can actually, when you look at this, this is really 2 inequalities in one. It's x is greater than or equal to 2 and x is less than 6. But some compound inequalities you can't represent the way I represented those. So for instance, what if I wanted to represent the solution set that falls outside of a region involving 2 numbers? So for instance, what if I wanted to represent the set of everything less than or equal to 0 plus everything greater than or equal to 5. Now this U right here stands for the union. It's the union of 2 sets. So the word for that, a literal word for union, is OR. So we want everything in this set or plus everything in this set. Now since this set says everything less than or equal to 0, then I would give this, and notice I got the bracket with the 0 because 0 is part of the solution, and then I've got everything to the left of 0, so that goes to negative infinity. And then x is greater than or equal to 5, that I would start with the bracket on 5 since 5 is part of the solution, and then everything to the right of 5 would go out to infinity. And notice the graph here, notice it starts here at 0, and notice I have the closed circle. Again, you could put a bracket there if you wanted to. The closed circle and everything to the left of 0 represents that first set, but the solution also includes everything greater than or equal to 5. So here I bubble in the 5 with the closed circle and then shade everything to the right of the 5. Now if I wanted the same set but I didn't want to include the numbers, then I could say x is less than 0 union with the set x is greater than 5. And of course that would just mean that I would put parentheses here with the 0 and parentheses here with the 5. And then on the graph I would have the same graph, except now notice I'm using an open circle to show that 0 is not part of the solution here, but I'm still shading everything less than 0. And then over here an open circle to show that it's not part of the solution, that 5 is not part of the solution, but you shade everything to the right of 5. And then again, I won't do both of these, but I'll just do one of those. If we wanted to include one, like say we wanted to include the 0, we could say x is less than or equal to 0. And then if we don't want to include the 5, we could say x is greater than 5. And so on the interval notation, that would be negative infinity to 0 with a bracket, but it would be 5 to infinity with the parentheses by the 5. And then to shade, since the 0 is included, we would bubble in the circle at 0 and shade everything to the left. And then since the 5 is not included, we would do the open circle here at 5 and shade everything to the right. Now again, you could use the brackets here and the parentheses here like we did before. Again, it just depends on what your instructor prefers to see. Now, I want to cover a couple of other sets, and these are sort of the kind of opposites of one another. If your solution is all values on the number line, then in set builder notation that would be x such that x is an element of reals. In other words, that means x is all real numbers. Okay, so that basically just means all real numbers. And interval notation to represent all real numbers is you just say from negative infinity, comma, plus infinity, and that tells you that we include everything on the number line. Now notice this number line it's all shaded in green. The entire number line is shaded, so that implies that the entire number line is the solution. Another set would be the empty set, and so this represents the empty set. And another way to represent the empty set is just a set of empty braces, and the empty set means that no values on the number line are part of the solution set. So if you look at this number line, there's no shading. All you see here is the number line. So that's how you would shade the empty set. Okay, so now I want to convert set builder notation to interval notation. So if you want to convert x is greater than 1, less than or equal to 3, that would be a parentheses at 1 and a bracket at 3, and then this represents everything from 1 to 3, but it doesn't include the 1, it does include the 3. This one is a union of everything less than or equal to negative 2 with everything greater than, excuse me, greater than or equal to 5. And so everything less than or equal to negative 2 would be negative infinity to negative 2 with the bracket, and union with everything greater than or equal to 5 would be 5 to infinity with the bracket. The bracket because these two include the values. And then for all real numbers, I just showed you that minus infinity to infinity. And then here's interval notation, and if you want to write that in set builder notation, that would be from negative 4 to 0, but not including 0. So in set builder notation, that would be x is greater than or equal to negative 4, but less than 0. And then this one, negative infinity to negative 2 bracket means x is less than or equal to negative 2, and then union with 1 to infinity, that's x such that x is greater than 1. So it's everything less than negative 2, but including negative 2, plus everything greater than positive 1. And then let me just show you these real quick. I'll do 1 and 3 first, since those are easy to show you right here. So if I wanted to show n is greater than negative 3, I would start at negative 3, but since negative 3 is not in the solution, I would use an open circle and then shade everything to the right of negative 3. Now if I want to represent the set between negative 2 and 4, but include the negative 2 and not include the 4, then I would go negative 2 to 4 there. So I had to take a quick break there and fill that in because that should be bubbled in right here where the negative 2 is because of the greater than or equal to. And then the 4 is not bubbled in. So you shade everything between negative 2 and 4, and you bubble in the negative 2, but you don't bubble in the 4. Okay, so now the last couple here, if you want to shade x is less than 3, then you would do an open circle at 3 and then shade everything to the left. And here, if you want to graph everything less than negative 3, then that's an open circle right there. It's kind of hard to see, but everything less than negative 3, so open circle, then shade to the left, along with everything greater than or equal to 1. So since that's greater than or equal to 1, that would be a closed circle there, and then you shade everything to the right. So on this set, the solution set is everything less than negative 3, this region, plus everything greater than or equal to 1, which is this region. And again, if you don't like the open circles, you can put a parentheses here and then put in a closed circle. For closed circle, you can put a bracket. Okay, so now that should give you a pretty good taste of what interval notation is, and we can move on to actually solving these linear inequalities now.